section we will be discussing esters via alpha alkylation. This is very similar to things that we have studied in derivatizing ketones at the alpha position. Okay. So there we had used, or acids in the alpha position, there we had used what? The acid to acetic ester synthesis or malonic ester synthesis. So here also we will say that deprotonation of an ester at alpha carbon with strong base can be done, such as LDA, and gives a nucleophilic enolate, and that can be alkylated with a unhindered, again that means methyl halide or primary halide or secondary halide. So these are the common terminologies that we are constantly using while doing reactions. So let me present one scheme over here. Suppose this is your ester and we have used the LDA, and obviously this is my alpha carbon. So enolization takes place. So this is the ester enolate, and then one can think in the second step we are reacting the following with the alkyl halide, and that should lead to the formation of an ester that is derivatized at the alpha carbon. So out here one can think of mechanistically that this is the ester, base is taken to deprotonate it. So this is the deprotonation step that should lead to the formation of the ester enolate. And will give us our product, and the mechanism that is being used over here is SN2 type. So the electrophile is either, as I said, methyl 1 degree or 2 degree, but never your 3 degree. Rather, I should say let this be methyl and 1 degree. So that is how the alpha alkylation can be done. Now in the next step we will be discussing the retrosynthesis of esters which are alkylated at the alpha position. So one of the possible methods over here can be by disconnecting the ester or the what we can say is disconnecting the alkyl group that is joined at the alpha carbon. Okay, So what we can think of is this is our ester molecule. Now this particular carbon is the alpha carbon, so we are saying disconnect from the alpha carbon. Okay. This is the group that we are disconnecting. So this group or carbon was the electrophile from R prime X, that is the alkyl halide, right? And if that is the electrophile, the other one has to be nucleophile. That means this carbon, that is the alpha carbon, was the nucleophile. That is the ester enolate. Okay, this is our target molecule. So our synthons over here are going to be RO and the minus charge over here. So this we are calling as our nucleophile. And the R plus we are calling as our electrophile. Synthetic equivalents, when we are thinking about that, it will be this ester out here plus the LDA, and the other one has to be the alkyl halide, which is having the electrophilic alkyl group. So that is one method. So in this method, what we can say to summarize the fact is that the retrosynthesis of an ester we have begun with the disconnection of the alkyl group from the alpha carbon, and hence the alpha carbon will be the nucleophile, that is our enolate, and the carbon that was disconnected from the alpha carbon will be our electrophile, that is Rx. So the reaction of this ester enolate with the Rx will be involving a SN2 type backside attack, and hence over here the alkyl halide that we are going to use has to be a unhindered alkyl halide to avoid any type of elimination reaction. The other alternative procedure that we can think of over here is the use of a malonic ester, which will again involve the steps of deprotonation, alkylation, hydrolysis, and decarboxylation. Okay, so let's present that scheme. So again, suppose that is our ester. To introduce or before introducing the malonic acid ester, we will do a functional group interconversion and convert this ester into an acid, and things become very much known to us, which we have covered previously. So this is our alpha alkylated acid, and for such acids the disconnection procedure is to break the bond between the alpha carbon and the alkyl group. So this is our electrophile, and then obviously we will say this is going to be our nucleophile, and we are disconnecting at the alpha carbon. Okay. So for that, the synthons that we will get will be of this kind. Again, this is our nucleophile because it is carrying the negative charge, isn't it? And R prime plus is going to be our electrophile. And then we will write the R prime X as to be our synthetic equivalent carrying the electrophilic center. And we know from previous discussions that the synthetic equivalent for a acid enolate is going to be this particular molecule. That is the enolate of manolic ester. This is going to be a nucleophile. So what we can say now, that the reaction of this particular carbon with this R, which is again going to follow a SN2 type of reaction. So our R prime again has to be either a methyl or a primary alkyl halide to avoid any type of elimination products. Okay. Now, as a synthon over here, this particular molecule is better than the one over here. Why so? We will say that although this particular synthesis is going to be a longer one, because after these two react, we have to carry out the processes of obviously hydrolysis that will give you the acid part, that is this one. Okay, I mean, if this is going to react with that one, then obviously we have to do hydrolysis and decarboxylation, and then finally this one will react with the ROH to form the alpha alkylated ester. So this is a long route, but even though it is a long route, what we will say that this particular starting material is more resonance stabilized than this one out here, and hence what we will say that this particular process, the second one, will be higher yielding process and will be our preferred route of practice than the first one. Okay, so I hope that clarifies the topic of ester, in which we have discussed the retrosynthesis of ester. So thanks for listening. Have a great day and keep visiting Sarvasa classes for further in detailed lectures on the topic of retrosynthesis. This is Dr. Sarkar saying goodbye. and have a great day.